Hello, welcome back to Chemistry, It Is All That Matters, and today we're going to talk about Lewis dot atoms. So far we've learned to arrange our electrons based on Bohr molecules or Bohr atoms, and then we looked at electron configurations, and then we simplified that to noble gas or core notations. And then we looked at what are called orbital notations of how the electrons are arranged in the different levels of the orbitals. And now what we're going to do is we're going to take those orbital diagrams and we're going to turn them into what are called Lewis dot diagrams, where we're going to represent the symbol of the element surrounded by the dots to represent the orbitals. And in this case, we are only going to worry about the valence electrons. And we remind ourselves that the valence electrons are the electrons in the outermost orbitals, S and P, of the highest energy level we achieve in the electron configuration. So basically, it's the S and P that follow the noble gas notation. So if we get to an element like potassium, we're only going to deal with the 4s1 electron. We are only going to deal with the S and P orbitals of the highest energy level. So let's start with the most basic of the atoms, and that would be hydrogen. And we know that the electron configuration for hydrogen is 1s1. So that means we have one arrow representing the electron in the s orbital, and that is a positive spin electron. And that tells us that we have one electron in hydrogen's Lewis dot diagram. So that's pretty basic. So let's move on. Let's look at boron. Boron has a valence shell of 2s2, 2p1 because its electron configuration is 1s2, 2s2, 2p1. We're dealing with 5 electrons, but only 3 of them are considered valence electrons. The valence electrons being the highest energy level, in this case the second energy level, and we're looking at the s and p orbital. So for boron, we're going to put an electron in the first s orbital, and we remind ourselves that you have a second electron, and we have to put those in opposite spins, so therefore we have one up arrow, one down arrow. Once we have the s orbital filled, we can then go to the p orbital, and in this case we're going to put one electron in the first p suborbital. That means we have 3 valence electrons. So for the Lewis dot for this, we put one electron on top, we put a second electron on top, those are the s electrons, and then we put the third electron to the right, and this is the Lewis dot for boron. Moving on to carbon, and I'm going to do carbon even though it's very similar to boron. I'm going to do carbon because carbon has a special instance, a special case. Both carbon and silicon will follow this practice. So when we look at carbon, 1s2, 2s2, 2p2, valence shell is 2s2, 2p2. We're going to take the first electron, as we did before, and fill the s. And remember, Aufbau's principle says we have to fill the s orbital before we fill the p's. And then we move on to the p's, and remember we have to put one electron in each suborbital before we pair, so we put one in the px and then one in the py. Now, where carbon is a little different and silicon is a little different is they like to balance their electrons. By balancing the electrons, it means we have bonding in all of these suborbitals. And that's why what we're going to do is we're going to actually take this electron out, and we're going to move the fourth electron actually to the pz. And what this allows us to do in the Lewis dot diagram is we will have one on top, one on the right, one on the bottom, and one on the left. Now what this basically means is we now have 4 empty spaces, which means carbon can bond on all 4 sides. And that's why carbon is so important to life molecules like carbohydrates, fats, lipids, and proteins, because it's this ability to bond on all 4 sides, making long chains or forming rings that makes carbon invaluable to the organic material that makes up living organisms. So once again, carbon and silicon will both have this special case where that s electron will actually jump up to the pz and will balance out one electron in each suborbital. Therefore, the Lewis dot diagram has one electron on each side. So let's look at fluorine. And when we look at fluorine, we have 1s2, 2s2, 2p5, making 9 total electrons. But for the valence shell, we're only looking at the 2s2 and 2p5. So we're going to fill the s electron orbital first. Remember, Aufbau says we have to fill the s before we fill the p. So once we've filled the s, we can now start filling the p. And remember, we have the Hund's rule, which says we must have a positive spin electron in each suborbital before we pair. So we have to have an electron in each suborbital before we pair. And then the Pauli principle tells us that no two electrons can have the same 4 quantum numbers, so therefore we cannot have 2 electrons identified in the same space, so that's why we have a positive spin electron and a negative spin electron. So here we have fluorine showing 7 electrons in the s and p orbital of the second energy level, and the Lewis dot would give us 1, 2 on top, those are the s. Then for the p, we fill them in as we did with the electrons in the orbitals, 1 on the right, 1 on the bottom, 1 on the left, and then we pair back to the right and down to the bottom. So basically what we see here from fluorine is fluorine has 1 empty space. And this is why fluorine wants to take on an electron, which would allow it to follow the rule of octet and become stable like a noble gas. And that's why fluorine readily takes on electrons and has such a high electronegativity. So if we go to the third energy level and we do an example here, we're looking at phosphorus. So we're looking at 1s2, 2s2, 2p6, 3s2, 3p4. The valence shell are only the 3s2 and the 3p4. So likewise, we fill that in by putting 2 electrons in the s suborbital. We then fill each of the up electrons in px, py, and pz. And then we will pair the electron in the px to give us the 4p electrons. And our Lewis dot would have 2 on the top, 1 on the right, 1 on the bottom, 1 on the left, and then we pair the 1 on the right. Now, how many empty spaces does phosphorus have? Phosphorus has 2 empty spaces. It is looking to add 2 electrons and would readily become a -2 charge anion. Calcium. Calcium is 1s2, 2s2, 2p6, 3s2, 3p6, and 4s2. For the valence shell, we are only looking at the 4s2, so it's going to have 2 electrons in the s, 1 going up and 1 coming down. Again, they must have opposite spin according to Pauli's principle. We cannot put them up in the p suborbitals because of Aufbau's rule that we have to fill the s before we fill the p. And this would give us 2 electrons on top, representing the Lewis dot diagram for calcium. Now calcium has 6 empty spaces, so would calcium rather give up those 2 and become positively charged, or would it rather try to pick up 6? Well, of course calcium would rather give up 2, and that's why calcium readily will become a +2 cation. So if we go into the transition metals, remember we're only looking at the valence shell, so when we get to that 3d6 for iron, we're actually going to drop back and only look at the 4s2. So for valence shell and Lewis dot structure, we are only going to deal with that same process of having 2 electrons in the s orbital. So iron will have the same Lewis dot diagram as calcium. In fact, all of the transition metals will follow that same rule, and in their natural state, they're going to try to be +2 cations. So this was an introduction to how we draw Lewis dot diagrams for single atoms, and later we'll take these Lewis dot diagrams and actually create molecules when we combine formula matter in especially covalent molecules, and how we can show that they will share their electrons in those empty spaces. So keep working on your chemistry.